In probability theory and statistics, skewness is a measure of the asymmetry of the probability distribution of a real-valued random variable about its mean. The skewness value can be positive or negative, or even undefined. The qualitative interpretation of the skew is complicated. For a unimodal distribution, negative skew indicates that the tail on the left side of the probability density function is longer or fatter than the right side. It does not distinguish these shapes. Conversely, positive skew indicates that the tail on the right side is longer or fatter than the left side. In cases where one tail is long but the other tail is fat, skewness does not obey a simple rule. For example, a zero value indicates that the tails on both sides of the mean balance out, which is the case for a symmetric distribution, but is also true for an asymmetric distribution where the asymmetries even out, such as one tail being long but thin, and the other being short but fat. Further, in multimodal distributions and discrete distributions, skewness is also difficult to interpret. Importantly, the skewness does not determine the relationship of mean and median. Introduction. Consider the two distributions in the figure just below. Within each graph, the bars on the right side of the distribution taper differently than the bars on the left side. These tapering sides are called tails, and they provide a visual means for determining which of the two kinds of skewness a distribution has. Negative skew. The left tail is longer. The mass of the distribution is concentrated on the right of the figure. The distribution is said to be left-skewed, left-tailed, or skewed to the left. Positive skew. The right tail is longer. The mass of the distribution is concentrated on the left of the figure. The distribution is said to be right-skewed, right-tailed, or skewed to the right. Skewness in a data series may be observed not only graphically but by simple inspection of the values. For instance, consider the numeric sequence, whose values are evenly distributed around a central value of. We can transform this sequence into a negatively skewed distribution by adding a value far below the mean, as in e.g. Similarly, we can make the sequence positively skewed by adding a value far above the mean, as in e.g. relationship of mean and median. The skewness is not strictly connected with the relationship between the mean and median. A distribution with negative skew can have the mean greater than or less than the median, and likewise for positive skew. In the older notion of non-parametric skew, defined as where micro is the mean, u is the median, and sigma is the standard deviation, the skewness is defined in terms of this relationship. Positive, right non-parametric skew means the mean is greater than the median, while negative, left non-parametric skew means the mean is less than the median. However, the modern definition of skewness and the traditional non-parametric definition do not in general have the same sign. While they agree for some families of distributions, they differ in general, and conflating them is misleading. If the distribution is symmetric, then the mean is equal to the median, and the distribution has zero skewness. If, in addition, the distribution is unimodal, then the mean equals median equals mode. This is the case of a coin toss or the series 1, 2, 3, 4. Note, however, that the converse is not true in general, i.e., zero skewness does not imply that the mean is equal to the median. Paul T. von Hippel points out, many textbooks teach a rule of thumb stating that the mean is right of the median under right skew, and left of the median under left skew. This rule fails with surprising frequency. It can fail in multimodal distributions, or in distributions where one tail is long but the other is heavy. Most commonly, though, the rule fails in discrete distributions where the areas to the left and right of the median are not equal. Such distributions not only contradict the textbook relationship between mean, median, and skew, they also contradict the textbook interpretation of the median definition. Pearson's moment coefficient of skewness. The skewness of a random variable x is the moment coefficient of skewness. It is sometimes referred to as Pearson's moment coefficient of skewness, not to be confused with Pearson's other skewness statistics. It is the third standardized moment. It is denoted gamma1 and defined as where mu3 is the third central moment, mu is the mean, sigma is the standard deviation, and E is the expectation operator. The last equality expresses skewness in terms of the ratio of the third cumulant kappa 3 and the 1/5 power of the second cumulant kappa 2. This is analogous to the definition of kurtosis as the fourth cumulant normalized by the square of the second cumulant. The skewness is also sometimes denoted skew x. The formula expressing skewness in terms of the non-central moment E, x3, can be expressed by expanding the previous formula. Properties skewness can be infinite, as when, or undefined, as when. In this latter example, the third cumulant is undefined. One can also have distributions such as where both the second and third cumulants are infinite, so the skewness is again undefined. If Y is the sum of n independent and identically distributed random variables, all with the distribution of x, then the third cumulant of Y is n times that of x and the second cumulant of Y is n times that of x. So, this shows that the skewness of the sum is smaller, as it approaches a Gaussian distribution in accordance with the central limit theorem. Note that the assumption that the variables be independent for the above formula is very important because it is possible even for the sum of two Gaussian variables to have a skewed distribution. Sample skewness for a sample of n values. A natural method of moments estimator of the population skewness is where is the sample mean. S is the sample standard deviation, and the numerator M3 is the sample third central moment. Another common definition of the sample skewness is where is the unique symmetric unbiased estimator of the third cumulant and is the symmetric, unbiased estimator of the second cumulant. In general, the ratios n are both biased estimators of the population skewness. Their expected values can even have the opposite sign from the true skewness. Nevertheless, and each have obviously the correct expected value of 0 for any symmetric distribution with a finite third moment, including a normal distribution. The variance of the skewness of a random sample of size n from a normal distribution as an approximate alternative is 6n, but this is inaccurate for small samples. In normal samples, has the smaller variance of the two estimators, with where m2 in the denominator is the sample second central moment. The adjusted Fisher-Pearson standardized moment coefficient is the version found in Excel and several statistical packages including Minitab, SAS and SPSS. Applications. Skewness has benefits in many areas. Many models assume normal distribution, i.e., data are symmetric about the mean. The normal distribution has a skewness of 0, but in reality, data points may not be perfectly symmetric. So, an understanding of the skewness of the dataset indicates whether deviations from the mean are going to be positive or negative. D'Agostino's chi-squared test is a goodness of fit normality test based on sample skewness and sample kurtosis. Other measures of skewness. Other measures of skewness have been used, including simpler calculations suggested by Carl Pearson. These other measures are Pearson's first skewness coefficient. The Pearson mode skewness, or first skewness coefficient, is defined as standard deviation. Pearson's second skewness coefficient. The Pearson median skewness, or second skewness coefficient, is defined as 3 standard deviation. The latter is a simple multiple of the non-parametric skew. Other starting from a standard cumulant expansion around a normal distribution, one can actually show that skewness equals 6 standard deviation plus O. One should keep in mind that equalities above given often don't hold even approximately, and these empirical formulas are abandoned nowadays. There is no guarantee that these will have the same sign as each other or as the ordinary definition of skewness. Quantile-based measures. A skewness function can be defined, where f is the cumulative distribution function. This leads to a corresponding overall measure of skewness defined as the supremum of this over the range 1/2 u less than 1. Another measure can be obtained by integrating the numerator and denominator of this expression. The function gamma satisfies -1 gamma 1 and is well defined without requiring the existence of any moments of the distribution. Galton's measure of skewness is gamma evaluated at u equals 3/4. Other names for this quantity are the Bowley skewness, the Yule-Kendall index and the quartile skewness. Kelly's measure of skewness uses u equals 0.1. L moments. Use of L moments in place of moments provides a measure of skewness known as the L skewness. Distance skewness. A value of skewness equal to 0 does not imply that the probability distribution is symmetric. Thus there is a need for another measure of asymmetry that has this property. Such a measure was introduced in 2000. It is called distance skewness and denoted by d-skew. If X is a random variable taking values in the d-dimensional Euclidean space, X has finite expectation. X is an independent identically distributed copy of X, and denotes the norm in the Euclidean space. Then a simple measure of asymmetry is in d-skew equals 0 for X equals 0. Distance skewness is always between 0 and 1, equals 0 if and only if X is diagonally symmetric, and equals 1 if and only if X is a non-zero constant with probability 1. Thus there is a simple consistent statistical test of diagonal symmetry based on the sample distance skewness. Grainer-Veldon-Meedan's coefficient Grainer-Veldon-Meedan have suggested, as an alternative measure of skewness, where mu is the mean, u is the median, is the absolute value, and E is the expectation operator. Med-couple. The med-couple is a scale-invariant robust measure of skewness, with a breakdown point of 25%. It is the median of the values of the kernel function taken over all couples such that, where is the median of the sample,